Now, welcome to the next lecture of signal processing. This lecture we will start with some examples. And the first example asks us to determine the Fourier series. Determine the Fourier series of the signal xt equals sine of omega t. So, first of all, we can use the formulas that we have seen the previous lesson, which are these ones. In this case, we would use this one. However, since we would have sine and an exponential, it would be difficult as we need to do integration by parts, and it will be a little long. That's why I will show you a different version of how we can solve this. First of all, we can try, as we have derived the Euler's equations before, we can try to add up these two values. And as we know, this one will equal to cosine negative j k omega plus I times sine negative j k omega minus cosine j k omega plus I sine j k omega. And then, as we know, this minus over here can be eliminated, because the negative of an angle and the positive of an angle give the same cosine value, so we can basically see this as plus. And then this minus sign will go outside, and we will put it here. And then as we do the all the algebra in here, we will see that it will equal to minus I sine j k omega minus I sine j k omega. That's why if we divide it by minus 2j, it will give us the value that we wanted. So we can basically say that sine omega t equals to e to the power of j k omega t minus e to the power of j k omega t over minus 2i. So we need to find the coefficients, as we need to find the value of a, the coefficients of Fourier series. And so a minus 1 equals to minus 1 over 2j, because we can separate these two and it will give us this. Minus 2i, and the k value will give us the, I'm sorry, there's no k here. The k value is the subscript of a. So here we have k equals minus 1, so that we have the minus sign in front, and here we have k equals 1, so that it is multiplied by plus 1. Here it is multiplied by minus 1. Here it is multiplied by plus 1. So in this part, k equals minus 1, we are writing it here, k equals minus 1, and the coefficient is 1 times minus 2j. All right? And then similarly, a plus 1 equals minus 1 over minus 2j, which gives us 1 over 2j. And that's it. And we have a 0 equal to 0, because we don't have any value, so it means it was a to the power of 0, and it gave us 1, and so that we didn't show it. And now let us see the second example. Example number 2, and it asks us, it gave us a signal such as this. And the question asks us to find the Fourier series coefficients. Find the Fourier series coefficients. This one we will again apply the previous method that we have used in the previous example. So in order to have a 1, we need to have e to the power of 0, I. So we will basically do e to the power of 0, I, plus, in order to have the sign value, we need to make e to the power of minus omega t I. I'm using I instead of j in this example in order to see both writing styles. Minus over minus 2i, as we have seen in the previous example, plus it will be multiplied by 2 because we only know this part, and will be multiplied by 2 by the coefficient, and we will add these two and divide it by 2. Similarly, we will write e to the power of I omega 0. Omega 0 in this case, it is the whole expression over here, this one, and plus pi over 4 plus the negative of this expression, as I will write it over here, 2 omega 0 t plus pi over 4 plus e to the power of minus I 2 omega t pi over 4 over 2. Okay, and here we are. We actually wrote it in the Fourier series. However, we are asked for the coefficients, which we can easily find it, as we can write it we can write the above expression as 1 plus e to the power omega 0 t I, and we will take it into parentheses, this part. Let me see. We have it here, we have it here, and that's it. So we will write it into parentheses, and it will give us 1 over 2j, 2i, sorry, plus 1. Plus, we will write the next element, which is e to the power of 2 omega ti, and let me see where we have these expressions. We have it here and here, so let me write the coefficients of these values. E to the power of pi over 4 over 2. And similarly, let me write e to the minus omega ti, and I am again writing the coefficients with the same method. And let me write the let me continue from here, as I don't have any space left. E to the power of minus 2 omega ti, and let me see the coefficients again with the same method. We have the coefficients which are here. I'm sorry, the previous thing that I said was wrong, but here we have minus sign. That is why we are now including this part here. E to the minus pi over 4 over 2 is the coefficient. So here what we have is a 0 equals to 0, because e to the power of 0 gave us 1, which we have it over here, and a 1 is 1 over 2j plus 2i plus 1. A minus 1 is minus 1 over 2j plus 1, A2 is e to the power of pi over 4 over 2. E to the minus 2 equals e to the minus Now let us continue with the next subject, which is convergence of Fourier series. Convergence. Now, Fourier at the time claimed that any periodic signal could be maintained by using Fourier series representation. This is today is found out that is not quite the case for every periodic signal, but for a majority of signals this is true. So for which ones this is true? Now let us see this one. First of all, the signals which have finite energy over a single period, then this is verified, it is true. Let me write it here, signals which have finite energy. And we can show it like this. The square of the signal should be less than infinity, should be finite. If this is guaranteed, then we can say that the coefficients are finite. Okay, now let's move on to the second. Over any period, x of t must be absolutely integrable. Over any period, x of t must be absolutely integrable. So we can show it like this. Over any period t, that's it. Next condition is in a finite interval, there are no more than finite number of maximum or minimum points during any single period of signal. So the third condition is in a finite interval, there are no more than finite number of maximum or minimum points during any single period of signal. Don't worry, I will give examples for each one at the end. Now for the next one is any finite interval of time, there are only a finite number of discontinuities. Let me write this too. Now let me give an example for each one. And for example, this signal over here, which we have asymptotes, and it is like this. This one violates the first one, because it says over any period xt must be absolutely integrable. I'm sorry, for the second one. Over any period xt must be absolutely integrable. However, in this part, since the signal goes to infinity, it is not absolutely integrable here. And let me move on to the next one. And for example, if we have an example like this, where it goes like this. Now in this case also the rule is violated, because the first one here we see in a finite interval there are no more than finite number of maximum minimum points. However, here as we can see, there are a lot of maximum and minimum points. Here I couldn't give exactly the thing, but in the if we were to draw this graph in Desmos or another graphic place, we would see that it is actually there's so much that they are uncountable, like this. So this violates the rule. And for the last one, we can give an example like this. If our graph goes like this, and it is uncountable in this part, there infinite number of discontinuities, which violates the rule. Now let me move on with the next subject, which is 3.5. Before that, let me give you the main nature of the Fourier series. Unlike these graphs, these three graphs, we can see that the Fourier series can be used to approximate many periodic signals, including square wave signals. Square wave signals are like this, but even though they are square, we can approximate these by periodic signals such as sine, cosine. So how do we do that? With n equal 1, we would have a signal which approximate the signal like this. With n equals to 3, we would have a approximation like this, which is even more approximate. With n equals to, as n grows larger, let's say n goes larger as n goes to infinity, it grows smaller and smaller. And at the end, we would have a value which is very close to the square wave like this. So it goes closer and closer to the real periodic signal. Now let's move on to the next subject, which is 3.5, properties of continuous time Fourier series. And here, suppose that xt is a periodic signal. Suppose xt is a periodic signal with period t and fundamental frequency omega, which is equal to 2 pi over t. Now let me write this down. Now if we have the signal xt and the Fourier series transform as at, now let us see how these change as different processes are conducted over these. First of all, linearity. If xt and yt denote two periodic signals with period t and have Fourier series coefficients denoted by ak and bk, let me show it like this. If xt and yt are periodic signals and have Fourier series coefficients, xt has ak and yt has bk as Fourier series coefficients, the new signal t and we have the new signal z of t equal a multiplication a with xt plus b times yt. It means that the Fourier series coefficients of z is the a multiplication by ak plus b multiplication of bk. Here ak and bk are taken from here. Let's move on to the second property, which is time shifting. So if we have a y signal and it is the t0 time shifted version of the xt signal, then what do? We already knew that for any ak, which means Fourier series coefficients, we need to use this formula, 1 over t integrated over t, xt times e to the power of minus j n omega t dt. So instead of xt here, we will instead write this one. And then instead of t, we will write t minus t0. And let me change it. Let me write ak equals 1 over t times integrated over t x t minus t0 e to the minus j k omega t dt. I'm sorry, we will not write it, we will not change it. It will remain like this, and we will use a different technique, as I will show now. And instead of t minus t0, we will write tau, and t will equal tau plus t0. And let me write it this time. Instead of t, we will write t0 plus tau. And we will write it as seen x tau. This time I wrote tau instead of this expression, and times e to the minus j k omega tau plus t0 dt. All right, and then let me open this parenthesis and write like this, dt. And as we can see here, if we only see this part, it is exactly the same as a k, so we can basically put this one out in front of the integral and see the results. And as we can see here, just the dummy variable changed. So we can write this as ak. And that's why we can basically see that it is equal to the same value of Fourier series coefficients times e to the power of minus j k omega t and t0, the value that it was shifted with. And I also wanted to emphasize that here we have dt, and then by taking the derivative of both sides, dt equals d tau plus 0, because t0 is a coefficient, so we will write dt and d tau, they are the same. That's why after this part I wrote d tau here. I just wanted to emphasize this, as I forgot in the previous part that I was explaining. So the takeaway from this example was, as we time shifted this volume, the Fourier series coefficient changes, and it is just multiplied by this value, and this coefficient remains the same. And the only change was multiplying this with this value over here with the by not forgetting the time shifting value. Now let's move on to the next property, which is the third one, time reversal. So here we already know that the signal can be shown as this. We know this from the previous lesson. And if we time reverse this and we say we are going to see x of minus t, we know that it will go ak times, instead of t we will write minus t, so let me put it like this. And we already know that omega omega 0 was equal to 2 pi over capital T, which gives us the period. So it is also equal to pi over t. Great. Now, what we are going to do here is that we are going to make a substitution. We will write k equals minus m, and let me show it here. K equals minus m. Let k equals minus m, and we have another signal y of t, which is equals x of minus t, and we have m equals minus infinity to infinity a minus m e to the power of j m 2 pi t over capital T. So it is seen that the signal is completely same. These parts are completely same with the above expression, which is this one. The only difference is that we have a minus index and here we have a positive index. So we have, we can write it like this. So basically what we need to have as takeaway is that when we make time reversal, we just change the subscript of the coefficient. X of minus t gives us Fourier series coefficients a of minus k. And we have Fourier series here. The Fourier series coefficients are like this. So this is the key takeaway that we need to take out from this part. In other words, time reversal applied to a continuous time signal means that time reversal of corresponding sequence of Fourier series coefficients. So here we need to analyze two things. What happens if the signal is odd? What happens if the signal is even? Now let us see this. Xt, if it is even, then x of minus t equals x of t, right? Then it means that a subscript to the subscript minus k equals to a subscript k. Here, if xt is odd, then we can say that x minus t equals to the minus of xt. So we can say that a subscript minus k equals minus a subscript k. And this is an important property that we should keep in mind. Now let us see another property, which is time scaling. So if we were going to do time scaling, let me write it here. Time scaling. Then we need to write x of alpha t, which means that we need to write alpha t instead of the value t in the previous formula that we have seen in the previous lesson. Let me write it here. K equal from minus infinity to infinity, ak times, as you remember, we used to do it like this, but instead of t, we will write alpha t. That is the only difference. So here, as we can see, there's no difference in the coefficient, but the nature of the signal has changed because the exponential has changed. Now let us move on to the next property, which is multiplication. Let me write it multiplication. Now in multiplication, let me write directly the formula, as the derivation part is really long. Now we have xt if the Fourier series coefficient of xt is ak, and if the Fourier series coefficients of yt is bk, then we can say that if xt and yt is multiplied, the Fourier series coefficient is obtained as L going from minus infinity to infinity is equal to A subscript L to B K minus L. Okay, this is the method that we will apply. And now let us move on to the last property, which is conjugation and conjugate symmetry. Let me write it here. In this property, we have if xt has Fourier series coefficients as ak, we have xt conjugate has Fourier series coefficients as a minus k, and we have conjugate property. Here, notice we both have conjugate, and we have the minus k here, minus subscript as the time reversal. Okay? Now let us move on to the next argument, which is Parsifal's relation for continuous time periodic signals. Now let me write this down super fast. This property tells us that 1 over t integrated over t is equal to the sum of k goes minus infinity to infinity, the coefficients. And one should see that this is the average power. This equality is known as Parsifal's relation for continuous time periodic signals.